In the end, it's not important to make a building that stands for a long time, but it's important to really produce a process makes sense, even though if it is just a pavilion that stays there for just 1 week. The way we try to build this board, it's also to try to break this protagonist story and to try to see really the process that is behind it, because as we said, this is maybe the most important contributions of these experiences of structural physical models as we are discussing tonight. Yeah. And maybe one way to do this is to really look at the process in the design process as we know it. So from the concept until the design development, the construction of it, the prototyping, and then the communication or the presentation to the public in exhibitions and so on. And we try to build this narrative. But of course, it's not a narrative that is following one specific project. It's not a narrative that is following one specific figure. And maybe nobody of them did all these different models, but each figure is important maybe for some specific things. In the first case, something that you can see on the left, they are mainly models to visualize or to represent something. And maybe this left part of the board that you see here, maybe these are the types of structural models that are maybe more similar to the architectural models as we know usually among our discipline. But maybe the right one is probably the most far from our architectural thinking, and they are really like machines. So they are devices that are somehow the outcome of specific technologies that flourished, especially during last century, that were developed on the one hand to generate forms, so to produce design, but on the other hand to verify these forms, especially to test their performances, structural performances in this case, and to define the dimensions of the single members.
And among of these key aspects, it's maybe interesting to start with the notion of the term model itself. And quite often the term model is not only used for a physical model, it's also used for a kind of principle or for a scheme or to describe an artifact or a concept. So to say it simple, a model is a kind of simplified depiction of the reality. Probably the way of simplifying in most cases happens through the scale. So the reduction of scale helps to simplify and to focus on a specific problem. And when we simplify the scale, or when we reduce the scale, we also have to consider that this affects the materials. For example, if you test something in reinforced concrete, as you can see on the picture on the right side, you cannot take the normal steel reinforcement that you would take in scale 1:1. You also have to scale down the material properties, the strength of the material, that it's in proportion to the scale of the model.
The notion of scale, which is, let's say, intrinsic to the concept of model itself, it's very interesting that obviously it acquires an incredible importance in the architectural domain. But as you say, the structural domain adopts the idea of scale in a completely different way, right? So it's not just about reproducing an object or selecting the information that it provides, but it's really about the physical behavior somehow. It's about the performance, no, of the object itself, all the way to somehow the material qualities of it.
Yeah, and maybe also the picture that we have pointed out here with Lukas, it's probably the most famous structure that Sergio Musmeci developed. And this specific, the specific picture refers to the model testing that was developed in a special national center in Italy.
They took a microconcrete that has exactly these conditions of proportionally being 10 times weaker, and also the reinforcement, they took like a kind of weak steel, and probably they also took a steel mesh that is less dense, but this I'm not sure. Either they fully scaled down the material property, or they chose a network that is a bit less dense, that you have the same, let's say, amount of reinforcement per square meter, like in real, just scaled up 10 times.
Yeah.
And maybe this one brings us back then to the failure characteristic, because in that case, the model was really brought to the collapse of it, to really test what was the strength of this structure, but also in terms of to understand what was the ultimate load condition.
Yeah.
Which
I mean, this is really one of the key points, no? That the structural model is made to be broken, and this is obviously a fundamental distinction, no? With any other kind. But there is a kind of intrinsic life and death of the structural model that let's say belongs to its own reason to exist.
I have one suggestion about this issue of failure, because it seems to me that actually failure is the reason why, if I'm not wrong, but the reason why the science of construction was invented. Because basically they had to explain why building collapsed, broke. Isn't it true? Because you showed previously the example of the bone, the two bones, you know, which is a very kind of famous example. Although I never fully understood, this comparison. This comes from Galileo's discourses, right?
Yeah, this example from Galileo addresses the comparison of two animals. And let's consider they both have bones, and these bones have more or less the same properties, the same strength. So it's clear that when you have a mouse, the bone can be very slender to carry the light weight of the mouse. But in the case of an elephant, the bone doesn't increase its strength. It's more or less the same like in the case of the mouse. Therefore, the bone of the elephant has to be way thicker. This is maybe the most simple way to explain it.
Yeah. That's why basically by scaling something, you create the monster. So you cannot scale a man because his bones are not going to, their strength is not enough, right?
Yeah, exactly.
You carry the load. So basically you become a monster suddenly when you're scaled. That's what the stuff is about.
Yeah, and also because you cannot, you can infinitely almost scale maybe an object. You know, an animal can be 10 millimeters or 10 meters. But you cannot infinitely scale the property of the material, the strength, how much load you can apply on such a bone, or not in the same manner, let's say.
Yeah.
You have the same, for example, also in buildings, often large buildings like bridges, that you say you cannot build a concrete bridge that is infinitely long. This is not possible, because on a certain moment, even though we have the highest strength concrete, it will not be possible anymore to withstand the loads. It will be too thick then, no?
Yeah.
Yeah, but also then again with the material properties of the physical models is really important, this, because especially in the models that are developed to verify the things, that are maybe these ones that we can see here, that are a bit the ones that we can call machines, or the complex ones. In this case, the material is really crucial. So for example, in the case of Heinz Isler, that is maybe the example that I know more, that is the Swiss engineer that he was using these types of models for his reinforced concrete shells. In this case, he was using plexiglass, because plexiglass has a ratio between stress and strain that is quite comparable with the one of concrete. But when you bring then, and you use then the other types of models to collapse, so to really understand until which limit you can really design, then in that case, maybe you have to go closer to the actual material of the real of the full scale building. So of course, in this case, if you want to design something in reinforced concrete, then you use probably micro concrete.
It seems to me that the 20th century physical model, which is in a way a relatively recent development, if you think about it, really seems to have been developed together with the science of materials. So with the study and understanding of the physical properties of all of these compounds that you were talking about, right? So the physical properties of gravel, of sand, of steel, obviously, because in a way, building a structural model is a design process in its own right. It's a structural exercise in its own right.
Yeah, maybe this one is especially important for the point that we call the laboratory or somehow setting, because in some cases, maybe for the models that are developed for design, the structure, maybe in that case, it's more a laboratory or an office where maybe the designer is either alone or with a small group of people. But especially when we have these more complex models that are the verification models, then it's quite important to have a collaboration among different disciplines, many different institutes, people, and especially also the support of public and private institutions. So, for example, we with Lukas, we decided to put here this picture that is a picture showing Fray Otto in front of one of his models of that he designed at the Institute for Lightweight Structures in Stuttgart. And maybe this one is the best example of this kind of collaboration, because Fray Otto was an architect, but at the same time, he was the head of an institute. And this institute, it was within the University of Stuttgart.
I was surprised that I didn't hear the term experiment when you addressed the laboratory. So I'm wondering if there are also different notions of experimentation.
I mean, it depends a lot on the case again. And again, and maybe this was also not so much introduced in the beginning, is that, or that is part of this notion that a model doesn't need to be physical only. It can also be, for example, mathematically described. And many of these tests that we will show today were mainly conducted not because you could not develop such a thing mathematically, but it would be very complex and very time-consuming. So the model was just a simpler and also more adequate way, and also at the end, the way that you probably trust more, because you really rely to physical conditions and not only to a theory. But I think this span between theory and empiricism, this is really depends then also how precise the model is conducted or the model test is conducted and how experimental you are. There are protagonists like Musmeci, for example, who had often also a mathematical approach in mind, and that solved the main problems through equations, and then only for specific problems used, for example, the subfield models to visualize a specific problem. Instead, Isler, as far as I understand, or also maybe Giulia can then elaborate a bit more on that, for him it was really an experimental tool or also an empirical tool, when you want to call it like that. So he really derived the form through the physical model and not, didn't rely so much on mathematics, or also later didn't rely so much on the computer.
So maybe at this point it would be interesting to mention a question that's, I mean, we were thinking about quite a bit, which is about the authorship of these models. I mean, you mentioned the idea of collaboration, which is clearly fundamental, no, for somehow the development, both theoretical and practical, of these objects. But I would be curious to hear a bit more about the logistics behind the actual manufacturing, because it does seem like a truly like a very complex manufacturing process, right, in its own right. Again, so who made these models, and how were they somehow designed, but also physically built?
So maybe maybe we can a bit make a differentiation between the design structural models and the verification models.
Okay.
In both cases, the question of the authorship is quite important, and maybe the main result of the design part is that, and probably the main difference from this kind of structural approaches, other than the more common architectural physical models, is that in these cases of design, the form was actually the output of the process. So it was not the part of the concept that was the great architect was developing out of his knowledge and his background and so on, but it was more a physical process that was reproduced scientifically, or to different degrees of scientifically, according to the different people that were doing it. But in the end, the form was generated through this process that most of the time is called form finding. But then in some cases, we have the geometrical approaches that were based mainly on mathematical equations.
So, yeah, I think this is the main aspect, how precise you develop such a test, or how much the precision is needed. And I mean, this brings us also back to maybe the question of the institution, or of the setting, and of the authorship, because I mean, the most extreme cases, there was Otto on the one hand, who had this lab with 10, 15 people at the university. And I mean, Musumeci conducted his soap film model tests at home at the kitchen table together with his daughter. So there are these two extremes. And it's not because he was less professional, but he used these means for a different reason.
Yeah. Is it fair to say that let's say the mid 20th century, so let's say during the 20th century, it's also the time where, I mean, in a way, structural engineering becomes somehow prescribed. So the mathematical modeling and all of its outcomes, or more sort of official prescriptions, become an integral part of structural design. For example, through the publication of manuals or books of this sort, and if that's the case, somehow the physical model can play against that. Now I feel like there is a level of, as you say, not only efficiency, and so a simplification that comes in with making a model instead of working out the equations, but also there's a level somehow of intuition that comes into modeling and manipulating matter that is somehow again that somehow challenges the abstract model, as Lukas, as you were saying. So in a way, these two forms of modeling are actually incredibly different. No?
Yes, I think it has mainly to do that it arises in 20th century because the structural solutions developed get way more complex. And to give you a simple example is, for example, all these shell designs. I mean, reinforced concrete comes up, and it makes sense to use it for walls or shells or domes. And this is quite difficult to tackle then the inner stresses in such a structure. The question of the manual, I think, comes up quite early in the structural engineering sciences, from the beginning of, I mean, from the foundation of the polytechnic schools. Mm-hmm. And this is strongly also a topic throughout the 19th century already.
Yeah, and also the fact that maybe in civil engineering, the established procedure was this analytical thinking. So basically all this history of the structural models that flourished in the 20th century has a lot to do with the first developments that were developed in other disciplines of engineering. Mm-hmm. So for example, the very first measuring model were developed for hydraulic engineering of dams. And there were congresses on this, or aeronautical engineering as well used a lot physical models. And it's not by chance that Fra Otto and Sergio Musumeci also studied aeronautical engineering.
This is really interesting, actually, because it somehow brings together this idea of codified design processes and in a way the afterlife of the model, because surely a structural model designed to respond to specific legal prescriptions has a different afterlife, no? Or can have a different afterlife than a model designed in the kitchen of your own house for the purposes of calculating or furthering your design process. So maybe it would be interesting to also hear a little bit about this, because it seemed also to be a crucial distinction between the structural model and the architectural model. No? The architectural model is something that in a way exists for its own sake, or can exist for its own sake, and so it can be stored, saved, sort of kept for posterity as also a form of documentation. It can be, kept to showcase or to demonstrate a certain design process, and so on and so forth. But the structural model doesn't behave like that at all, right? It has a completely different reason to exist, as we were talking about before. So what happens to these structural models after they are made and used?
I mean, maybe there is a nice anecdote about it from Isler, so that maybe these measuring models that it's one of the ones that we have seen before. So it's these measuring models or verification model that was developed during the design process of it. And it refers to probably the most complex building that is a shell building in reinforced concrete that Isler built in Geneva. And so he developed this model, he built the shell, but then Isler was a kind of very special person in this case, because he was really somehow experimenting throughout his entire life and his entire career. So he, in this case, since it was a very complex shape, he decided to take measurements of the built shell every year. Okay. Until his death. And this was built in 1967. He died in 2009. So it's really a long time controlling the deformation and the long-term deformation of the shell. Yeah. But he was always keeping this kind of measuring model in his office, not just because it was a nice object to show to the clients or to the people that were visiting his office, but because as soon as every time that he was going on the shell to measure the shell and the deformations on the real shell, then he was going back and he was using again and again his measuring models in plexiglass to see and compare the measurements on the shell and the measurements on the small scale model.
I mean, if I'm not wrong, these kind of physical models were made for huge public buildings, for instance, stadiums, or they are less common for houses. Sometimes we find them applied to pavilions, small pavilions, but there is not the kind of relationship with the program. This is a very architectural relationship. Mm-hmm. So there are no typologies, for instance, but you simply here you have shells, and then they cover large spaces. Mm-hmm. I mean, did you find some correspondence between programs and models?
Well, at least I would say that maybe in this case we don't really have architectural typologies, but more typologies in the way the process is generated. Yeah. So that also the way these people were communicating their projects and they were writing about them were making a differentiation that was following somehow these processes of generation of the form. So there were, Isler, for example, was calling the pneumatic shells, the ones that he was generating with these inflated membrane. Mm-hmm. So he was doing this experiment, and then he was producing this kind of buildings. And these were most of them were industrial buildings, but in his publications and in his presentation that were done in the public, he was not calling this is the industrial typology. He was calling this is the bubble shells, because the process behind it is a pneumatic process for him. So maybe the main generator was the causality law. somehow, so that what was the process to reach that specific shape.
Yeah.
And this is a quite contemporary concept if we look back at what Lukas was showing us.
I think it's very interesting because what you say, it's really about somehow switching the perspective or switching the way in which we categorize or classify architecture. It's really all about the way in which we look at these very common concepts that we architects use a lot, which, I mean, for example, typology, program, and so on. And it's really about finding out new ways of looking at these objects.
This technology, or this technique rather, was not invented by Otto or by Isler or by Musumeci. They actually came across that from mathematics. I mean, the interesting thing is these experiments pop up in these works all around 57, 58, 59, of all of them. This is quite interesting, and it's quite difficult to tackle why. But actually, it started 200 years before in the science of mathematics. So if you have a boundary frame in space, not planar, in space, and you want in this boundary frame to obtain the surface with minimal amount of surface, this became a mathematical model that was developed over 200 years. Was then also called the Plateau's problem, that took until the 30s to solve it. And for example, in the 30s, there was in Germany this school of mathematics in Göttingen, with David Hilbert, for example, was a famous mathematician who also used to work with soap-fill models to describe his theories on minimal surfaces.
A very short question only, maybe it's also obvious if the relation between the materiality or the performance of the material is always related to the scale. So I just thought, for example, cement is, you cannot scale it down. Cement has a capacity to get with water and stones together, concrete, but you cannot scale the resilience of cement, and maybe also from steel. I was just wondering if the two are always in a relation to each other, if you know what I mean.
Yes, I mean, you can scale it a bit, like this Musumeci model is 1 to 10. This is possible that you take a bit of weaker cement or you take a mixture that is less good, but for sure you cannot do a test like that in 1 to 100. This is not possible. That is exactly what you're saying. Yeah. And I mean, the matter of scale is also interesting, maybe in terms of the soap-fill model. And they're very small because when they become larger, the gravity would become a governing factor, and they would obtain a different form. Yeah. And because they are done quite often, not always, but quite often for surfaces that have almost no self-weight, like these tents by Frei Otto, they are with cable, they are quite light, or very light actually. You don't want this effect of self-weight become a governing factor, and therefore you keep them so small that really the surface tension itself remains the governing factor.
No, but also then the question of the measurements come in, so, because you can do a lot of experiments with the soap.
Yeah.
You visualize the shape in the end. But, since it's a material that is not really stable, you cannot draw on it. You cannot...
Exactly. This is the question. This is why I was asking, because surely it's a great way to visualize the object, but obviously it has some intrinsic problems. It's traditionally very, very ephemeral, let's say.
Well, Frei Otto dreamed to have a spray that you can spray on the surface and it will get hard, but that didn't happen. And Giulia, you maybe want to introduce the device here.
Yeah, and it's maybe the difference between Frei Otto and the constellation that Frei Otto had at his disposal at the University of Stuttgart, and what was different from other people who decided then to go with other methods because they were not really able to measure these things. And Frei Otto then developed one machine, and then this is the most advanced one. It took almost 20 years to develop it properly. but it was a sort of climatic chamber, so that you could generate the soap film inside it, and you could control the humidity in it.
Okay.
So the soap film that was generated in this minimal surface geometrical constellation, then in this climatic chamber was more stable than outside. And this period of that he gained through this machine was allowing him to take photographs of this soap film. And the photographs were done usually with Cartesian grid in the back, and they were done with parallel light, so that it was a sort of early photogrammetric tool to really be able to measure then the...
You have a parallel projection, basically, a kind of elevation. Yeah. That's amazing. Yeah.
And with this, he was then able to transfer the different geometric data that he was gaining through his really scientific experiments, and then refining further the shell and the shape of it in the further steps of the design. Yeah.
I mean, did you find experimentation with localities? Because this seems to be a very global, let's say, way of making architecture. It seems to really create a tabula rasa, you know, that you can transfer the same knowledge from place to place, and more or less you find the same thing. But actually, I'm interested if you ever find physical models made or experimented with local materials somewhere, you know.
I mean, Israel was doing experiments in his garden with the ice, because in Switzerland it's very cold in winter, and so he was doing experiments with textile membranes and then spraying water on it and then waiting during the night that the structure was then stable. But it was more a play for him, or a hobby, let's say, than...
I was thinking that actually one of the great things about structural models is that they exist to document, as Andrea was saying, and as we were also saying, a history of failures. And this is something that architecture has consistently avoided somehow. Architecture is a history of success. It's traditionally, you know, a collection of great achievements. And we have this very somehow additive history where, you know, we add on everything that has been done with further and further. And it's very selective in that. And I feel like actually this is exactly somehow the opposite thing, is documenting what doesn't work. And what doesn't work becomes even more important than what does. And I think the structural model is there to somehow document that as well, right?
Yes. I mean, it's a very beautiful observation about this failure and success. And at the same time, it sounds like a paradoxon, but quite often this, let's say, history of structural engineering or construction history, or however you want to call it, follows a quite positivistic narrative, and also quite, let's say, along one trajectory. And in a way, this is maybe the paradoxon that, because, I mean, why is it doing that? Because it's taken for granted there is always a kind of improvement of the solutions, so that you can achieve larger spans, you have higher material strengths, you have a faster building process. So the question of efficiency becomes very dominant in this sense. Efficiency in whatever kind. It can also be in terms of cost. And in a way, what you say now is really like a beautiful paradox situation, because when engineers are writing their own history, not always, some are, but it happens that it's quite often quite positivistic.
Yeah. But at the same time, a culture of experiment entails inevitably that failures have to become are fundamental, right? And you can't just dismiss them or pretend like it was on purpose or whatever, right? It has to be accounted for and it has to be used. So it somehow has to be put forward. And I think it's very beautiful that structural models are there to do exactly that, no? To break.
But another issue that you can observe as a development in the late 20th century and early 21st centuries, maybe these are absolutely the wrong examples for that, but that structures tend to have way more redundancy than before. I mean, in these shells, if you remove one of the supports, you will have a failure. But nowadays exists, I mean, the Kulas building, if you take out 2 or 3 of these struts, you will not have a failure at all. Maybe it's now too simple to compare in this way, but generally to say structures today have way more redundancy. So it's not anymore about this purity of a form that is obtained. The purpose why you're doing that, I mean, we also have to see that arose in the post-war period, in the early post-war period, and reached this peak in the 60s and the early 70s. And in this time, labor was quite cheap, but material was expensive. So it really was worth to develop forms that are efficient in the terms how they use material, but they were labor intensive. I mean, producing all this formwork was labor intensive. And all that obviously changed throughout the 70s and the 80s. So labor became expensive, and also planning was going for less riskful solutions.
I have one, let's say, to me, from my point of view, final remark, because it is about digital outcome. Because if we say that the future of physical modeling is the digital modeling, then it seems that what we discussed this evening is kind of a vintage, right? So I think that is not like that. I would say, and this kind of suggestion came to my mind when I saw Buckminster Fuller. You know that Buckminster Fuller was one of the references for the whole Earth catalog. That was subtitled "Access to Tools," you know? And what is very important, and I think that Giulia said a very important thing, that the Waller's catalog and Buckminster Fuller and all these kind of practices are based on procedures and the possibility to achieve a certain knowledge, not by the means of examples, as happens in 19th century handbooks, which are mostly catalogs, but here you have procedures. And I think that the potential, I see a strong potentiality in this physical modeling, although they dates back to the 70s. It is actually to providing people with the possibility to build their own shelter. Or if we imagine urgency or very catastrophic scenario, I think this is a very strong potentiality to become a source for procedures and practice to build. Because of course, all the digital modeling becomes very useful for huge public buildings, huge developments, and huge stuff. But when you, if you transfer this knowledge to the individual, really the primitive hut, logier, the primitive hut in the forest. This kind of knowledge that is embedded within the physical model can become very crucial to provide the individual with the knowledge to build his own shelter, his own, let's say, building in the end. Isn't it true?
Yeah, absolutely. And maybe it's also the differentiation between the models that we call the verification models and the one that we call design. Because in the case of the verification, for example, a lot of handbooks or manuals were produced and published by people that really defined the technique and the protocols to follow for this specific measurement technique. So dividing the different methods that were used, dividing the different technologies that were used, and really explaining step by step what to do and which technique to adopt for which specific condition. But this is somehow, it's a sort of a history in its own, and maybe is a very specialized sector of it. On the contrary, the procedure that were more accessible also for the broader public, and maybe it's also the the reason why these people became also famous to the broader public and were also studied by architects and not just by engineers is that because the principle behind it is very simple, and the way you produce it somehow theoretically is very simple, or seems to be very simple. Then in the end, you need really a lot of experience, you need a lot of precision to really do a very precise experiment to be able to replicate and do these different physical models to really be able to build your structure. But theoretically, the principle that is behind it is really simple, and you can really communicate in an easy way to a person that also doesn't know anything about engineering or architecture.
But I think I'm not sure if Andrea, this digital analog discussion has anything to do with the easiness of construction or not. On the contrary, I would say the certain digital models at least emancipate and allow the construction of very complex structures more easily.
This you can already see in the 50s. It's beside the easiness, it's also really playfulness too. And the playfulness, I mean, we can describe it empirically, but it's also just the willingness to, the will to go as far as possible and to branch out in so many different directions and to try out things. So it's a very playful approach, and this you can see in many of the digital projects also today. Not so many of them are structurally motivated, they are more like constructive or assembly motivated. This again has a bit to do with what I said before about redundancy and so on. I mean, the example of block and of block what we have seen with the shell, for sure, this is a structurally motivated example that is very much in line with what Isler did, or also what Otto did. Instead, the things on the right-hand side are rather about, sometimes even about new materials, or about processing materials in a new manner, where robotics, for example, comes into play. If you move a bit right, yes. I mean, not Dante Bini, but all the other more recent things. And I mean, what is interesting is that these concepts arise mainly at universities. So in a way, clearly that's research, but another thing that probably still also belongs to university, and this again addresses the issue of simplicity, is the aspect that it's a very intuitive method to use physical models. And to train intuition, I think this is really a reason why such kind of techniques might also stay in a curriculum of many universities. I mean, maybe we can show on the bottom. I mean, this also has a long history. On the one hand, there are these carpenter connections that are already. I mean, the models are done to train carpenters, or also what you can find at almost every school are these stabile-labile experiments dealing with equilibrium and somehow demonstrating equilibrium that we also know from the sculptures of Calatrava in a very highly polished way, or maybe even in a more spatial and refined manner by these sculptures by, or let's call them installations by Fischli Weiss. And they became also, in a way, here art becomes a key reference for training structures. And the intuition there is a very, very present. And I think this is also something that will always remain. Yeah. Either we will find the same of a kind of intuitiveness through digital means, or we will link the two domains. But for sure, we want to keep that somehow. This is something that will remain for sure.